In this video, we will understand the concept of buoyancy. Okay, so what is buoyancy? If you see the text on the right side, which is the content of the NCRT book or the NIOS book, so the upward force which acts on an object. And when does it act on the object? When the object is submerged in a fluid. This is known as the buoyant force. Okay, so we can take an example. Suppose we drop an wooden object into the water. Then we see that the wooden object floats in the water and a small portion of the wooden object lies within the water or lies submerged within the water. The total wooden object is not within the water, but a small portion of it lies above and another small portion lies below. Similar to the scenario C, which I have drawn on the screen on the left side, which is a floating object, partially submerged. On the other hand, if I drop a stone in the water, it will go all the way till the bottom of the uh, water body and remain at the bottom. So we say it has sunk to the bottom, which is similar to the scenario B. And if we can think of objects that don't totally sink to the bottom, at the same time they don't float on the surface, they remain somewhere inside the liquid, submerged. That is scenario A. So we will understand this buoyancy principle in terms of these three scenarios, because these are the only possible scenarios whenever an object is placed inside a liquid. Okay, so now before we start, let us state the Archimedes principle. Archimedes was a famous philosopher, historian, who tried to understand this concept, why some objects float in water and why do they sink. And he stated a famous principle which is called Archimedes principle. So in italics it is written here, and it states when an object is submerged partially or fully in a liquid, the magnitude of the buoyant force on it is always equal to the weight of the fluid displaced by the object. So when any object is inside the liquid, whether scenario A, B or C, we have the forces acting on the object are nothing but upward force, which is the buoyant force, okay, and the downward force, which is the weight of the object. If both of them are equal, we see scenario A. If the weight of the object is greater than the buoyant force, then we see scenario B, where the object is sinking to the bottom. On the other hand, if the weight of the object is less than the buoyant force, then we see scenario C, when the object is floating with partial amount submerged inside the liquid. Okay. Now we will see these three scenarios in detail and understand the buoyant force. So what is scenario A? Object submerged inside the liquid. Okay. So let us draw the figure again. This is our vessel and this is the object somewhere inside the fluid. So we'll first draw the object and we will draw the fluid surrounding it. Now what are the forces acting on the object? We know it is weight of the object which tries to push it down, buoyant force acting on the object which tries to push it up. Now what is weight of the object, which is nothing but mass of the object into acceleration due to gravity. Here I have written MO as mass of the object. Now further, if we write mass in terms of volume and density of the object, I can say volume into density of the object into G. So for clarity, I will mention these terms here. V is volume of object, rho O is density of object, and G is acceleration due to gravity, which is 9.8 meter per second square. We have understood from the gravitational force chapter, right? Now let us develop this equation further. What is buoyant force? Fb is equal to as per Archimedes principle, weight of the fluid displaced by the object. So I'll write it here, weight of the fluid displaced by the object. So what is this weight? Weight is nothing but a force, which is a product of mass into acceleration due to gravity. Now let us say ml is the mass of the liquid to distinguish it from mo, which is the mass of the object we have understood above. So I'll write it here. ml is mass of not the entire liquid, but the liquid or fluid displaced by the object. Okay. Now, what is this mass of liquid? It can be understood as a product of volume of the liquid into density of the liquid into G. Now I have written V as volume of the liquid displaced and V as the volume of the object. You can understand that because object is entirely within the liquid, whatever volume of the object is there, that was occupied by the liquid before the object was placed. So can we say that volume of fluid displaced by this object in this case is entire volume of the object, and that is why we have written V in as the volume of the liquid displaced. Okay, so I'll write it for clarity. V, volume of fluid displaced in this scenario, is equal to volume of object is equal to V. So understood? So let us say this equation is 1. This equation we have named it as 2. Now at equilibrium both these forces are equal. So we can say V into rho O into G is equal to V into rho L into G. Right? From equations 1 and 2. Now what are the common terms in both sides of the equation? V is the common term, so it can be cancelled. What are the other common terms? G is acceleration due to gravity, it is also common. So when we remove this, we get rho O equal to rho G, or we can state this situation in a different way. When the density of object, I'll write it above, density of object, and here it is density of fluid in which the object has been placed. So when we have a situation wherein density of the object is equal to density of the liquid in which it is placed, the object will remain submerged somewhere inside the liquid. It will not sink to the bottom of the vessel. It will not remain floated at top surface of the vessel. Okay. Now let's understand the scenario B. What was scenario B? When the object sunk to the bottom of the vessel. So again we will see this situation from the beginning. So object sunking to the bottom. Okay, let us draw the diagram. This is the vessel. Okay, and we will first draw the object, and this is the liquid surrounding the object. The object has totally sunk to the bottom of this vessel. Again we have two forces here. One is the weight of the object and one is the buoyant force on the object. Here weight of the object is greater than the buoyant force, that is why the object has sunk. So can we say weight is greater than buoyant force in this case? Now when we say, and we can also write it like this, weight minus buoyant force is the net downward force. Okay, we can say like this, right? So let us first focus on this inequality. What is this inequality saying? What is the weight of the object? It is mass of the object into gravity, and it is equal to, what is the buoyant force? Buoyant force in any case will be equal to the weight of the fluid displaced by the object. So mass of the liquid displaced by the object into G. And if we develop this further, mass of the object is volume of the object, which was V, what we took in the previous case, and rho of the object and G, and greater than, what is the mass of fluid displaced? Equal to volume of fluid displaced. In this case also the object is entirely within the water, so the volume of the liquid displaced is equal to exactly volume of the object, right? So we will write V, and rho L for the density of the liquid and G. So if we eliminate the common terms, what will we get here? V and G are common on both sides of the inequality. So we get rho O greater than rho L. That means we can understand it as density of object is greater than density of fluid in which it is placed. In that scenario, object sinks to the bottom. Clear? All right. Let's now see the third situation, wherein the object is floating with partial volume submerged in the liquid. So we will understand the floating object. What is this floating object? Let us say we draw a vessel and we have an object which is at the top surface of the liquid. So this is the liquid surrounding the object. Okay. Now a portion of the object is lying above the liquid, this one, and another portion is lying within the liquid. Okay, so note that. So now we will develop the equation in this case. This is the weight of the object, this is the buoyant force, and in this case buoyant force is greater than the weight of the object, that is why object is floating. So we will write W less than Fp in this case, and when we develop this equation in terms of basic formulae, mass of the object into gravity is less than mass of the liquid displaced into gravity. Now this mass of the liquid displaced is not entirely due to the okay, when we talk about the volume, let's come to the volume, then we'll understand. So mass is nothing but here volume of the solid, which is V, what we took previously, into density of the solid into G. Now this is less than. This mass of the liquid can also be broken down into volume and density, but unlike in the previous two scenarios, when we developed ml as V into rho L when it was sinking at the bottom, and here also V into rho L when it was submerged, because in that case the entire volume of the object was inside the liquid in both the cases. Here it is not the case. So here ml is not equal to V into rho L, it is VL into rho L into G, and I will write VL separately here. VL is volume of liquid displaced by the submerged portion of the body. Okay, not the entire volume of the liquid. Okay, so obviously we can say here VL is less than the entire volume of the object. This we need to keep in mind. So now I will assign this as equation 1. From 1 again I will write the equation 1 for clarity. V into rho O into G is less than VL into rho L into G. Eliminating the common term which is G here, we can say V into rho O is less than V into rho L. Now, since VL is less than V or V is greater than VL, this quantity is greater than this quantity and still its product with rho O is less than the product of this quantity with rho L. That means what? That means, doesn't it mean that rho O is less than rho L? Density of the object is less than density of the liquid. Not clear? So let us take a small example of a value and see this. So let us say volume of the object is 10 meter cube, just for understanding, and volume of the liquid displaced by the submerged portion is 5 meter cube. That means the object is lying with exactly half its volume submerged in the liquid. So this is the solid and exactly half, assuming it to be a cube, only the bottom half is inside the liquid, top half is outside. So I can say VL is 5 meter cube. Now, what was the equation in the previous page? Inequality, sorry, in the previous page. V into rho O is less than VL into rho L. So, V into rho O is less than VL into rho L. Putting the values of V and VL here, we will get 10 into rho O is less than 5 into rho L. Correct? Now you might have understood the implication. Here 10 is larger than 5, and still when we multiply it with rho O, the product is less than when you multiply 5 with rho L. That means how it can be possible? Let us say 10 into 3 may be less than 5 into 8. So this 3, if I assume as rho O, this 8 as rho L, you are understanding. So when the product on the left side is less than the product on the right side, with one of the quantities greater than the other, okay, then obviously the second quantity, that is in this case rho O, it has to be less than rho L. Okay, that's how we can understand. So now we will develop this backwards. When you place an object in a liquid such that the density of the object we are placing is less than the density of the liquid, the object will float and only a part of it is submerged inside the liquid. When the So I will summarize these three scenarios now. This was our scenario A, wherein the object was lying submerged inside the liquid, correct? And this was the scenario B, wherein the object sunk to the bottom of the liquid, the vessel containing the liquid, okay? And the third situation is the object is floating and only a small portion of the object is inside the liquid, okay? Only partial amount of the object is inside the liquid. We will name these cases as submerged case, sinking or sunk object, and third one is floating. Okay, for the first case, what we got is density of the object is equal to density of the liquid. Second case, we got density of the object greater than density of the liquid. Third case, we got density of the object less than density of the liquid. So these are the three scenarios which can be explained based on the Archimedes principle. Now let's proceed further with the text. So another example of buoyant force is when we are having a hot air balloon. Now in the same case, instead of liquid, air is considered as a fluid, and if you see, the balloon is submerged in the air. And because balloon is rising, can we say it is similar to the case of floating? So why it is floating? Because the buoyant force acting upwards on the balloon is greater than the weight of the balloon which is trying to push downwards. Okay, if a balloon is stable at a certain height, that means both these forces are balanced and the situation turns to situation A, submerged. When somebody wants to come down and the balloon has to land, they will make the weight of the balloon greater so that it is greater than the buoyant force, but not very high, only marginally, so that the balloon descends slowly to the ground. So this is the concept of buoyancy and the floating objects. Hope you have understood this.